Hi everyone. Today we introduce a central topic of probability theory, the notion of independence. If you look at these two events, owning a car and owning a cat, you may say that they're independent. If I know that you own a cat, that doesn't tell me anything about whether you own a car or not, and vice versa. But owning a car and getting into a traffic accident, these two events are probably dependent. How can we express this mathematically? It is fantastic that mathematics is able to capture such a rich real-life phenomenon as independence. And today we'll find out how. Intuitively, we can say that two events E and F are independent if the occurrence of one event does not affect the likelihood of the other event. So E and F are independent if the occurrence of F does not affect the likelihood of E, and vice versa. Conditional probability can help us express this as a formula. If we know that F occurs, the likelihood of E is this conditional probability. And if E and F are independent, this conditional probability should be the same as probability of E. In other words, the occurrence of F does not influence the likelihood of E, and vice versa. Now let's rewrite these two formulas using the definition of conditional probability. By definition, conditional probability is this ratio. And also in the other equation, this is this ratio. Notice that formally I should have written probability of F intersection E, but intersection is symmetric. If we multiply both sides of this equation by P of F, and both sides of this equation by P of E, this equation becomes P of E intersection F equals P of E times P of F. And this equation also becomes that. So, surprise, both of these equations, they're equivalent to this equation. So these are saying the same thing, this. So we can take this equation as the definition of independence. Let's do it. We say that two events E and F are independent and denoted by this sign. It's like orthogonal to each other. If the probability of the intersection equals probability of E times probability of F. As a simple example, flip a coin 2 times. And let E be the event that the first flip is ahead, and F be the event that the second flip is ahead. Intuitively, the 2 flips of the coins should be independent. And let's check that by the formula. The sample space here has 4 outcomes. E intersection F is the outcome that both first and the second flip are heads. That consists of only one outcome, HH, out of 4. So this is 1/4. While the probability of E, that the first flip is ahead, has 2 outcomes. And so does the probability of F, that the second flip is ahead. So probability of E, probability of F is 2 out of 4, which is 1/2. And as we see, this equation indeed holds. 1/4 equals 1/2 times 1/2. So E and F are independent. One important warning: independent events are not the same as mutually exclusive events. In fact, these are completely different, almost opposite notions. Indeed, mutually exclusive events means that if one event happens, F, for instance, then the other event, E, may not happen because their intersection is empty. the occurrence of F does affect the likelihood of E very, very negatively. It excludes it completely. So being independent is not the same as being mutually exclusive. Great. Now we have the definition of independence of two events. What about three events? What about four events? When do we say that three events, E, F, and G, are independent? There are two natural candidates for such definition. One possibility is just to say that events E, F, and G are independent if all the pairs of them are independent. If E is independent of F, E is independent of G, and F is independent of G, which by this definition means that the following three equations hold. An alternative candidate for the definition of independence of three events would be to say that an analog of this formula holds for three events, which means that P of E intersection F intersection G equals the product P of E, P of F, and P of G. So which of the two candidates should we take as a definition for independence? The answer is we should take both of them. So we should say E, F, and G are independent if all of this holds, in which case we may say that they're pairwise independent, because that simply means that any pair of them is independent. And on top of this, this formula also holds. And that becomes a definition of independence of three events. You may say, oh my goodness, my head is spinning now. Why do we need this extra thing? Doesn't it automatically follow from here, from the pairwise independence? Actually, no, unfortunately. And here's a specific example where it happens. Consider the experiment where you pick a number between 1 and 4 at random and with uniform probability. So any choice of the four numbers is equal or likely, has probability 1/4. The sample space, S, is just the collection of the four numbers, 1, 2, 3, and 4. Now consider the following three events, E, F, and G. E will be the event that you picked 1 or 2. F will be the event that your picked number is 1 or 3. And G will be the event that your number is 2 or 3. So E is this event, F is this event, and G is this event. What's the probability of E? E has 2 elements out of 4, so that's 1/2. And so is probability of F and G. What's the probability of E intersection F? E and F intersect only in one element, 1. So that probability is 1/4. And as we see, this is the same as P of E times P of F, 1/2 times 1/2. So the definition of independence of E and F does hold. E is independent of F. And similarly for the other pairs, E is independent of G and F is independent of G. So taken together, this means that these events, E, F, and G, are pairwise independent. Are they fully independent? Does this hold? No. And that's because the intersection of E, F, and G, all these three events, is empty. There is no element, no number between 1 and 4 that belongs to all of these three events together. So the probability of this is 0. And it's not the same as P of E times P of F times P of G, which would be 1/2 times 1/2 times 1/2, which is 1/8. So while these events are pairwise independent, they are not fully independent. And that shows the reason why we included this extra formula instead of saying that maybe it just follows from these three. We just defined independence of 2 events and independence of 3 events. How do we define independence of 4 events, 5, 6? How do we define independence of any collection of events? We should include all such formulas with any combination of events: E and F, E and G, F and G, E, F, G, F, G, H, F, I, G, F, H, J, A, K. Any combination of the events should produce such a formula. And so the definition of independence is the following. Events E1, E2, E3, and so on are independent if the probability of intersection of any subset of them, which we'll define this way, equals the product of the probabilities, which I'll define like this. There could be any subset I. An important property of independence is stability. It says that you can make any operations on independent events and they still remain independent. More precisely, if we look at the collection of events E1, E2, E3, and so on, and F1, F2, F3, and so on, and if all these events together are independent, then whatever operations you do on the events E1, E2, E3, and whatever operations you do on events F1, F2, F3, these will be still independent. So any event formed of the E1, E2, E3 is independent of any event formed of F1, F2, F3, and so on. And by formed, we just mean that we can use set operations, intersections, unions, complements as many times as we want. So any combination of set operations is allowed. Now, because this theorem is so important in our practice, let's make an informal proof of this theorem. Let's check a couple of special cases first. Let's analyze the complement and prove that if E and F are independent, then E and F complement are also independent. Here's our sample space, which is partitioned into 2 mutually exclusive events F and F complement. And here is an event E. It may have some common part with F, specifically E intersection F, and a common part with F complement, specifically E intersection F complement. So E can be decomposed into this part and this part, which are mutually exclusive. Then the additivity axiom tells us that the probability of E can be computed as a sum of the probabilities of these 2 parts. By independence assumption, the first part equals P of E times P of F. That was the definition of independence of 2 events, E and F. Let's isolate this term and move everything to the other side. P of E minus this term. P of E is a common factor here. Let's take it out. 1 minus P of F. That's a probability of F complement. And we proved that E and F complement are independent. This was the definition of independence of 2 events. Probability of their intersection equals the product of their probabilities. So we proved that independence is stable with respect to the complement. Let's prove that independence is stable with respect to the intersection operation. So if E, F, and G are independent, then E is independent of F intersection G. By definition, all we have to do is to check that the probability of E intersection with this event equals the product of the probabilities. The probability of E intersection with that's just the intersection of all three. And by definition of independence, that was the product of P of E, P of F, and P of G. That was this contested equality that we decide to include in the definition, and now we know the reason why. Next, we can use that F and G are independent. And by definition, that means that their product of probabilities is the probability of their intersection. So we proved that E is independent of this event because the probability of their intersection equals the product of their probabilities. At this point, we showed that independence is stable with respect to these two operations, taking the complement and taking the intersection. And now let's just notice that any set operation can be built from complements and intersections. How do you build the union, for instance? You use De Morgan's law. De Morgan's law turns unions into complements and vice versa. So the union F of G, if we take another complement of both sides, is this. So the union can be built by repeating operations of the complement and intersection. Now we treated all set operations, complements, unions, intersections, and that's how we proved this stability theorem. This episode was unusually theoretical, and that is because we had to set the stage with the important notion of independence. Let's recap what we did very quickly. Two events are independent, if this holds. Many events are independent if a similar formula holds for any combination of them. Independence is stable in the sense that if you have independent events, then whatever you do to them, they will remain independent. Whatever set operations you do on them, the result will still be independent. In the next 2 episodes, there will be a lot of examples, I promise. So stay with me and have fun.